Welcome to this explainer. Today, we're taking what looks like a super intimidating, highly technical engineering graph, and we're going to translate it into a completely intuitive, incredibly powerful map. Because honestly, this is quite literally the exact map engineers use to understand and extract the energy that powers our entire modern world. All right, let's just dive right in. Imagine for a second you're drilling miles and miles beneath the Earth's surface. You're dealing with extreme heat, absolutely crushing pressure, and, millions of dollars on the line. You absolutely have to know what's down there before you bring it all the way up to the surface. Is it going to be oil? Is it going to be gas? How on earth do engineers accurately predict what they're going to hit when they literally cannot see it? Well, that is exactly where this map comes in. And here is that guide. We call it the pressure, temperature, or PT phase diagram. Think of this graph as the ultimate explorer's map for reservoir geologists. On the vertical axis, we've got that crushing underground pressure. And on the horizontal axis, that's our extreme temperature. By tracking just these two specific variables side by side, this diagram reveals the exact physical state of the fluids hiding down there at any given depth.
Okay, moving to section 1, the territories. Let's look inside the phase envelope.
Right smack in the center of our map lies the phase envelope. This enclosed region is essentially a mix zone. It represents the specific conditions where liquid and gas actually exist together at the exact same time. Now, if you move anywhere outside this envelope on the map, the fluid is entirely in a single phase, meaning it's either all liquid or all gas. But inside, that's where it gets interesting because it's a complex mixture of both.
And we can get way more precise than just saying, oh, it's a mix. Inside that phase envelope are these things called quality lines. Think of them kind of like the contour lines you'd see on a hiking map. They tell engineers the exact proportions of liquid and gas. So, as the pressure decreases, which means we're moving downward on our map, these lines show us exactly how the liquid fraction shrinks while the gas fraction simultaneously balloons. It's essentially a built-in, highly precise measuring tool right there in the envelope.
Now for section 2, borders and landmarks.
The absolute outer edges of our phase envelope completely dictate how a reservoir behaves. Up on top, we have the bubble point curve. That's the upper boundary. Here, the fluid is almost entirely liquid, and if you cross this line by dropping the pressure, the very first gas bubbles suddenly appear. Hence the name, right? Bubble point. On the flip side, the lower boundary is the dew point curve. Down here, the fluid is almost entirely gas, but cross this threshold and tiny liquid droplets start to condense out of the gas. Crossing either one of these borders absolutely changes the game for how that reservoir behaves.
But hey, what happens when these two curves actually crash into each other? Well, they collide at what we call the critical point. And this is a truly bizarre, extreme landmark on our map. At this one, highly specific pressure and temperature, there is zero distinction between liquid and gas. None. They just merge into the single, supercritical phase. All those standard rules of liquids and gases we learned in high school, they just blur together into something totally unique.
Now, if we push our map to its absolute physical limits, it brings us to a fun word, the Cricondentherm. This is the extreme thermal edge of our two-phase territory. It's the absolute highest possible temperature where a liquid and a gas can actually exist together as a mix. If things heat up even a fraction of a degree past this point, moving to the right on our axis, you are never going to see two phases coexisting again, no matter how much you mess with the pressure.
And of course, if there's a thermal limit, we naturally have a vertical pressure equivalent, the Cricondentbar. This is the absolute highest possible pressure where two phases can coexist. Once you go past this totally crushing pressure limit, moving higher up on the vertical axis, only one phase can ever be stable. So these two extremes, the Cricondentherm and the Cricondentbar, basically draw a box around the absolute limits of our phase envelope.
All right, section 3, classifying the reservoirs.
When we're trying to categorize this massive deposit of energy sitting miles beneath our feet, a single landmark, that critical temperature we talked about earlier, actually acts as the ultimate dividing line. It's brilliant in its simplicity. If the temperature of the entire reservoir is below the critical temperature, engineers generally classify it as an oil reservoir. But if it's hotter and sits above that critical temperature line, boom, it's a gas reservoir. It's just this incredibly elegant way to predict whether you're dealing mostly with oil or gas, long before production even ramps up.
Which brings us to section 4, real-world reservoir navigation.
Let's finally put this static map into motion. I want you to think of energy production as a literal journey straight across our diagram. Step 1 is the initial state. We're miles deep, pressure is sky high, and we're at a specific, constant temperature. Then step 2 happens. Extraction begins. As we start actively pulling fluids up and out of the ground, the overall pressure down in the reservoir gradually drops. But, and this is key, the temperature down in the earth stays pretty much exactly the same. Because of that constant temperature, our plotted point draws a perfectly straight vertical line right down our map. And step 3? Well, drawing that line straight down means we are inevitably going to cross borders. Specifically, we're going to intersect those critical bubble point or dew point curves.
And let me tell you, crossing those borders triggers some massive physical changes. Engineers have to navigate these hazards really carefully. Say we're in an oil reservoir, and our dropping pressure hits that bubble point. Suddenly, all this dissolved gas separates out of the oil. Gas liberation begins. Or what if we're in a gas condensate reservoir, and we hit the dew point? Well, then liquid actually starts condensing right there inside the reservoir itself. And that leads to a huge, highly dangerous hazard known as retrograde condensation, which can severely ruin how much hydrocarbon we're actually able to recover.
Let's actually zoom in on that specific term for a second, because understanding this is absolutely vital. Retrograde condensation happens when the pressure falls below the dew point, which causes extremely valuable liquids to literally condense right inside the porous rock of the reservoir. So why does this matter? Well, once those liquids condense inside the rock, they are stuck. They become physically trapped underground. If you misread your phase diagram and you accidentally let the pressure drop incorrectly, you can permanently strand highly valuable resources miles beneath the earth. Once they're trapped like that, you just can't get them out.
So the ultimate takeaway here is this. The map is the absolute key to maximum recovery. By deeply understanding these specific production paths on the PT phase diagram, engineers aren't just guessing. They can accurately predict exactly how that fluid is going to behave. This allows them to design brilliant, highly efficient extraction strategies that completely avoid traps like retrograde condensation. Ultimately, it ensures we optimize the reservoir's performance and squeeze the absolute maximum out of every single operation.
And that actually brings us to a pretty fascinating final thought for this explainer. We've mapped the phase envelope, right? We've plotted out the critical points, and we know how to navigate the major hazards. But human engineering literally never stops. As we push the absolute limits of deep earth extraction, drilling much deeper than ever before, into even higher pressures and way more extreme temperatures, what hidden boundaries are we going to cross next? What entirely new, strange behaviors of fluid dynamics are just waiting for us miles beneath our feet? Thank you so much for joining me, and keep exploring the complex worlds hidden right beneath the surface.